Conservative forces are a special class of forces with the following two properties. One, when conservative forces do work, they transform kinetic energy into stored potential energy and back again. We are going to talk about two kinds of potential energy here that I'm indicating by green and red for now. And this diagram is meant to capture that concept. So in the center, this icon represents a hardworking force, subscript C for conservative. So a conservative force that can do negative work to transform blue kinetic energy into one of these forms of potential energy. And we use the letter, a capital U, to represent potential energy, just like capital K represents kinetic energy. The U doesn't stand for anything. It's just a convention to use U for potential energy. So a conservative force can do negative work to remove kinetic energy from an object, slow the object down, and store that energy as potential energy, or the conservative force can do positive work to take some of that stored potential energy and transform it into kinetic energy to speed an object up. So this is the cycle of transformations that conservative forces can do when they do work. The second property is that the work done by conservative forces is path independent, which means that WC, the work by a conservative force, depends on where the object starts and where the object ends, but it does not depend on the path it takes in between. So an object starting at 1 and ending at 2, taking any of these paths to get there, well, if that object is being acted on by a conservative force as it travels, the work done by that conservative force would be the same along any one of those paths. The length of the path and the shape of it doesn't matter. The work done by a conservative force only depends on where you start and where you end. The first of two conservative forces we're going to talk about is one you're familiar with already, the force of gravity. It is our textbook conservative force. So here, if we've got this gem in free fall, traveling in this parabolic arc after it's been tossed through the air, from moment 1 to 2, the force of gravity on it, we can see is doing negative work because of that obtuse angle between the force of gravity and velocity. This diagram here shows our force of gravity doing negative work, transforming some of the gem's kinetic energy into this green gravitational potential energy, which we'll represent algebraically as capital U subscript G, UG for gravitational potential energy. That's as the gem is moving upwards from 1 to 2, slowing down but gaining height. The higher it is, the more of this gravitational potential energy it has. And then from moment 2 to 3, when the gem is on the way down, we see that the force of gravity makes an acute angle with the velocity. Therefore, it's doing positive work, speeding the gem up. So here's that force of gravity at that time. It's changed what it's doing and is instead now transferring gravitational potential energy back into kinetic energy via positive work, speeding up the gem. So there's the two phases of our cycle right there, kinetic into potential, and then potential into kinetic. A conservative force can do both things. And the equation we use to capture that is this right here. The work done by the force of gravity equals the opposite of the change in gravitational potential energy. That minus sign has to be there. That minus sign is key. It's there to remind us that when gravity does negative work, such as from 1 to 2, gravitational potential energy increases. UG increases when gravity is doing negative work. Therefore, we need a minus sign here. Likewise, from 2 to 3, in a moment like that, or along an interval like that, when gravity is doing positive work, UG is decreasing, losing UG. So when delta UG is negative, we need a minus sign out here to multiply it so we get a positive work. So the work done is always the opposite of the change in UG. Negative work corresponds to UG increasing, positive work corresponds to UG decreasing. So let's use this idea to now derive an expression, an algebraic expression for UG, for gravitational potential energy. If we're going to graph the y component of the force of gravity on this gem as it moves from 1 to 2, graph that as a function of y, then the graph is going to look like this. Here is the y coordinate of the gem at moment 1 and the y coordinate of the gem at moment 2. And our force of gravity on it is a constant negative mg that whole time. The y component of gravity is negative, so negative mg. There's our constant force of gravity from 1 to 2. And I've shaded in this magenta rectangle here. And the area of that rectangle we know represents the work done by gravity as the object moves from moment 1 to moment 2. So from y1 to y2. The area under the curve, or the area between the curve and the zero axis on this force versus distance graph, is the work done by that force. Now this area is beneath the zero axis, so we know it's going to count as a negative work. We find that area by doing the length of the rectangle times its width. So that's a length in meters times a width in newtons, or newtons times meters. That's a reminder that this area represents work because its units are newtons times meters, Newton meters, which is the unit of work. So FGY times delta Y, our length times width for the rectangle. The height here, negative mg, the width delta y, y2 minus y1, y final minus y initial, that's our delta y. So that's our expression for the area. If I distribute the mg and factor out that minus sign out front, I can write the work done by gravity as this. The opposite of mg times the final y coordinate minus mg times the initial y coordinate. And this expression written here reminds us of the principle we just wrote down above, that the work done by gravity is the opposite of the change in gravitational potential energy. And what we've got here is the work done by gravity equals the opposite of a final value of mgy and an initial minus the initial value of mgy, suggesting that mgy is the expression for gravitational potential energy that we've just been looking for. So we now define the gravitational potential energy, UG, of an object of mass m located at vertical position y. UG is defined as mg times y. Mgy is the gravitational potential energy of some object at some moment. We see how it depends on the height of the object. The higher the object is, the bigger the y value, the more gravitational potential energy the object has. So this expression here becomes the opposite of UG final minus UG initial, UG final, UG initial, or the opposite of the change in UG from 1 to 2. And we can see here that the work done by gravity is path independent, as promised, that it depends only on the initial and final values of y, not on the path taken. See, the work done by gravity just depends on final y and initial y. To calculate it, you don't need to know anything about where the object was in between or how long it took to get from y1 to y2, the shape of the path it took from y1 to y2. None of that matters. To find the work done by gravity, you just need to know where it started and where you ended. That is path independence.